Hello and welcome to this A-Level Maths exam paper walkthrough. This is for Set B, Paper 1 as part of the AJMaths A-Level Maths mock papers. Now feel free to use this paper almost as a 2024 predicted paper for the upcoming exam series. The questions and the material featured within this paper is based on the Pearson Edexcel specification for A-Level Maths. So the style of questions and the material featured within this paper should look pretty familiar. You've listened to these styles of questions before, but hopefully there is a good few questions in here that will give you a bit of a challenge and hopefully a good bit of revision. It is worth pointing out, please do not use this as your only source of revision. Obviously, this is just a mock paper. Do revise everything. Go check out our website, ajmaths.co.uk. We've got plenty of other revision over there, revision videos, worksheets, exam papers, so on and so on. Other than that though, I think that's everything that we need here to get started. So let's begin now with paper 1. Starting off then with the very first question here, question 1 for this paper. We're given that theta is small and measured in radians. Use the small angle approximations to find an approximate value of 2 theta tan theta over cos 4 theta minus 1. So a nice easy question here just to get us started. So we've got small angle approximations here and we're working with tan theta and cos 4 theta. So let me just start by writing down the small angle approximations for tan theta and cos theta. So if we start with cos theta then, so cos theta here, this is approximately 1 minus, so 1 minus theta squared over 2. Okay, so that's cos theta, that's the approximation. Now for tan theta, nice and straightforward, tan theta is approximately theta. Okay, so using these approximations here then, what do we have for 2 theta tan theta over cos 4 theta minus 1? Well, in that case then, I've got 2 theta times theta, because tan theta is approximately theta. So 2 theta times theta, and that's all over them. Now be slightly careful here with cos 4 theta. So the argument here isn't just theta, it's now 4 theta, but all that happens here then is we replace theta with this argument. So now it's 1 minus 4 theta all squared over 2. We've got 1 minus, so like I said then, it now becomes 4 theta all squared over 2. So 1 minus 4 theta all squared over 2. And then what we've got here is the minus 1. Okay, so minus 1 there at the very end. So now let's simplify. Well, 2 theta times theta, nice and straightforward. That gives me 2 theta squared. Now for the denominator here, I've got this 1 here and this minus 1 here. So they'll cancel straight away. So what that leaves me with then is minus, now we've got 4 theta all squared over 2. Well, 4 theta squared, that would be 16 theta squared. And that's over 2. Okay, so minus 16 theta squared over 2. That would just leave me with minus 8 theta squared. So minus 8 theta squared there. So from here now it's just a matter of simplifying. Well, I've got a theta squared here in the numerator, a theta squared here in the denominator, so they'll cancel. So now I get left with minus 2 over 8. And again, we can cancel down here to get minus 1 over 4. Okay, so the approximate value then of 2 theta tan theta all over cos 4 theta minus 1 is approximately minus 1 over 4, giving us a solution to question 1. Moving on to question 2 then, where we have the curve C, which is defined by the following parametric equations. We can see the given parametric equations here. And question 2 asks us to show that the Cartesian equation of the curve C can be expressed in this form here. So this is y equals ax squared plus bx plus c, where a, b, and c are integers to be found. So we've got another nice easy question here just to get us started with this paper. And like we can see, there's only 3 marks for this question. We shouldn't really expect too much work here. So where do we begin? Well, the easiest place to start here is with this equation then for x. So x equals t over 2 plus 1. What we're going to do here then is rearrange this and make t the subject, and then we can substitute that into this equation here. And from there, we'll obtain something of this form once we simplify. Like we said then, if we start with this equation here, so x equal to t over 2 plus 1. Now rearrange and make t the subject. So I'm going to start by subtracting 1 off both sides. So we get x minus 1 is equal to t over 2. And then from here, multiply both sides by 2. What we get then is t is equal to 2x minus 2. Now what we're going to do here is substitute that into this equation here. So y is equal to t squared plus 5. Well, if t is equal to 2x minus 2, we can now substitute that into this equation. So from here, we get y is equal to 2x minus 2 all squared plus 5. Now we'll expand these double brackets here. In that case then, we're going to get 2x times 2x, that's 4x squared. We then got 2x times minus 2, so it would be minus 4x. We also repeat that again. So minus 2 times 2x is another minus 4x. So in total there, we've got minus 8x. So minus 8x. And then finally, minus 2 times minus 2 is positive 4. So plus 4 there. Don't forget the plus 5 at the very end. And now if we collect like terms then, y is equal to 4x squared. We've got minus 8x here. And then finally plus 4 plus 5. That gives me plus 9 there. Okay. And what we've got now is something of the required form here. So in that case, then we can now easily identify the values of a, b, and c. So a is equal to 4. B is equal to minus 8. And then finally, c is equal to 9. And there we have it. So that gives us the solution there to question 2. Moving on to question 3 now, where it says, given your answers to 2 decimal places, solve the simultaneous equations. So we've got 2 equations here. I've got e to the power y equals x minus 2. Let's call this equation 1. And then we've got the second equation here, y plus 1 equals ln x plus 1. And we'll call this equation 2. Now, it's up to you where you begin with this question here. What I'm going to do for this question is start with equation 1, rearrange this and make y the subject, and from there I can then substitute that into equation 2, and then hopefully we want to solve for x and y. So let's rearrange equation 1 then, like we said. So to make y the subject here, I need to take the natural logarithm of both sides. So if we do that, we get y equals the natural logarithm of x minus 2. Like so. Then, like we said, we can now substitute this here into equation 2. If we do that, we get the natural logarithm of x minus 2 plus 1 is equal to the natural logarithm of x plus 1. Okay. Now, to make life a little bit easier here, I want to keep this 1 positive, so I'm going to subtract ln x minus 2 off both sides. So we get the natural logarithm of x plus 1 minus the natural logarithm of x minus 2. And this is equal to 1. And we can also make life easier again here by writing this as a single logarithm. So we can write this as a quotient then. So this is the natural logarithm of x plus 1 all over x minus 2. Okay. And this is equal to 1 again. Now, if we want to go on to solve for x and y, then what we need to do here is get rid of the natural logarithm. So to do that, we take the exponential function of both sides. So e to the power of ln x plus 1 over x minus 2, that just leaves me with what's inside the bracket here. So we get x plus 1 all over x minus 2. And that is equal then to e to the power of 1. That just leaves me with the right-hand side here being e, like so. And what I can do now is multiply both sides by x minus 2. So we get x plus 1. X plus 1 is equal to e times x minus 2. So what I want to do now is collect the x's on one side. So I need to expand this bracket here. So I get x plus 1 is equal to xe minus 2e. And then if we subtract xe off both sides, I'm also going to subtract 1 off both sides. What we get here then is x minus xe is equal to minus 1 minus 2e. Okay, let's keep going here. So I can now factor the x out here. So we get x lots of 1 minus e, like so. From here then, what I'm going to do is, well, obviously, we've still got the right-hand side, so minus 1 minus 2e, and now I can divide through by 1 minus e. Okay, so therefore x equal to minus 1 minus 2e all over 1 minus e. Okay, so what we need to do here is just put this into our calculator. So if we do this correctly here, what you should find then is we get 3.75. Okay, so we get 3.75 there for x. We now need y. So y here, well, we have a rearranged form for y. Don't forget y is equal to the natural logarithm of x minus 2. So y is equal to ln x minus 2. So if x is equal to 3.75, then y is equal to the natural logarithm of 3.75 minus 2. So we get ln 1.75. Just put this into your calculator here, and what you should find then for y is we get 0.56 there. Again, just make sure you give your answer to 2 decimal places, like the question asked for. Okay, so now it just asks for it to 2 decimal places here. We give x to 2 decimal places, and the same is true for y. Okay, but there we have it. It's like it's the solution there to question 3. Moving on to question 4 then, where we have the table below which shows corresponding values of x and y for y equals e to the power of the square root of x. So we've got our table of values here for x and for y, and we're then told that the values of y are given to 4 decimal places as appropriate. Now for the first part here, part A, all we want to do is use the Trapezium Rule to find an estimate for this integral here. Let's scroll down then. So for part A, we're simply going to use the Trapezium Rule. So the result that we need here, this is given in the formula, but you don't have to worry about memorizing this. So this is the integral then from A to B. So let's say we're integrating y here with respect to x, so y dx. This will be approximately h over 2, or a half h, whichever you prefer. We then times this by, so we take the first and the last y value, so we call that y0 and yn, and we add those together, like so. And then we take all the other terms, add those together, and then multiply those by 2. Okay, so we're going to take the first term here, or the first y value I should say, the last y value, we add those together, and then we take the remaining values, add those together, and multiply that by 2. So that's going to be plus 2 lots, so it would be y1 plus y2, and this would keep going all the way up to the penultimate term. Okay, so we call that yn minus 1. Okay, like so. So this result here will give us an approximate value or an estimate for this integral here. Okay, and don't forget for h here, this is b minus a all over n. Okay, so in this case here, h would be, that's going to be 2, because b is 2 for us here. We've got 2 minus a, which is 0. Then we divide that here by the number of strips. So in this case here, we actually have 4 strips. So we have 5 columns, but this corresponds to 4 strips. That's my first strip, second strip, third strip, and then the 4th strip here, the final one there. So we've got 4 strips in total, so it's 2 over 4. So we get a half there. Okay. So we put all this together then. The integral here from 0 to 2 of, what did we have? E to the power the square root of x. With respect to x then, this will be approximately, so it's going to be h over 2. Like we said, h for us is a half, so that's going to be a half divided by 2, so that will give us a quarter. We get a quarter there. We then got y0 plus yn, so my first term plus my last term. So my first, keep calling it a term, I mean y value. So my first y value is 1, my last y value is 4.1133. If we add those together, 1 plus 4.1133. Then we've got 2 lots of everything else. So 2 lots of these 3 y values here. So I put those in here. 2.0281 plus 2.7183, and then finally 3.4033. Okay. So now all we need to do here is evaluate this. So just use your calculator to evaluate this. And if you do this correctly, what you should find then is we get 5.35 there. Okay, and that is 2 free significant figures. Okay, So the estimate for this integral here is 5.3523 significant figures. So that's the first part complete. Now for the second part of this question here, part B, this is split into two parts. So I've got the first part here and then the second part. Now it says using your answer to part A and making your method clear, estimate these two integrals. So let's start with the first one then. So for B, part 1, we've got the integral, again from 0 to 2, of e to the power of the square root of x. Was it plus 4? Yeah, plus 4. And this is with respect to x. So this is kind of like a basic integration problem now. Can we simplify this integral here, or the integrand? So what we're integrating? Well, what I can do then is apply linearity here. We can split this up then as two integrals. We've got the integral from 0 to 2 of e to the power of the square root of x with respect to x. And we already know the approximate value of this. We evaluated that in part A. And I've also got the integral here from 0 to 2 of 4 with respect to x. Now this is a nice straightforward integral to evaluate here. This would be 4x. So this here is approximately 5.35. This is 5.35 plus this here. So that's going to be 4x. You get 4x there. Don't forget our limits here. So from 0 to 2. Well, 4x with these limits here, that's going to be 4 times 2, which is 8, minus 4 times 0. So that's going to be 0 there. So 8 minus 0 gives us 8 there. So what I've got here then is 5.35 plus 8. And that gives us approximately then, for this integral here, 13.35. Okay, so that's the solution to B part 1. And then for B part 2 here, again, pretty similar, same idea. We need to simplify this integral. So for B part 2, we have the integral from 0 to 2 of e to the power of the square root of x plus 2. Okay, again, with respect to x here. So we just take a look at the integrand again here. How can we simplify what we're looking to integrate? Well, it just comes down to basic rules then of indices. Because we're adding here, we can split this up as a product. So we can write this then as the integral from 0 to 2 of e to the power of the square root of x with respect to x. Sorry, let me get rid of the dx here. Done that a little bit too soon. We need to write it as a product, I should say. So now we can times this by e squared, because we're adding 2 here. So we can write that as a product like this. And now we have the dx here, like so. Well, e squared, that is just a constant, right? So we can apply linearity here and take this e squared outside the integral. So what I've got then is e squared times the integral from 0 to 2 of e to the power of the square root of x. Okay, well, we already know the approximate value of this integral here. That was 5.35. So what I've got here then, let me just write it down again in full. For the integral from 0 to 2 for e to the power of the square root of x plus 2 dx. Like I said, this is going to be approximately e squared times this integral here, but this is 5.35 approximately. So we've got e squared times 5.35. So just put this into your calculator here. And what you should find then is we get approximately 39.6 there. Okay, and that is to 3 significant figures as well. Okay, and there we have it. So that gives us the solution there to question 4. If we take a look now at question 5 here, where we have a question on proof by contradiction. So question 5 asks us to prove by contradiction that for all real theta, sine theta plus cos theta is less than or equal to root 2. Now with this being a proof by contradiction here, we need our opening assumption. What we're going to do here is assume. So assume that there is a value of theta. Assume that there is a value of theta. So we assume that there is a value of theta such that such that sine theta plus cos theta is strictly greater than root 2. Okay. Now, rather than working with, say, a square root here or a surd, so root 2, this is a surd, rather than working with this, we're going to square both sides to begin with. Okay. So if we square both sides here, we've got sine theta plus cos theta all squared is strictly greater than root 2 all squared. Okay. So sine theta plus cos theta all squared, that's your sine theta plus cos theta multiplied by sine theta plus cos theta. Okay, so if we expand these double brackets here, what we get then is sine squared theta. We'd also get a cos squared theta, so plus cos squared theta. And if you just think about these double brackets here, we're going to get sine theta times cos theta, and then we repeat that again, cos theta times sine theta. So in total, we've got plus 2 sine theta cos theta. Okay, and this is strictly greater than 2 then, because root 2 all squared is just simply at 2. Now from here, you need to notice we can use our trig identities, because I've got sine squared theta plus cos squared theta. Well, we know that that is identical to 1. So this bit here is equal to 1. So that's equal to 1. And then 2 sine theta cos theta. This is the double angle formula then for sine. So we've got plus sine 2 theta. Okay. And this is strictly greater than 2. So from here then, what can we do now? Well, I can subtract 1 off both sides. So if we do that, we get sine 2 theta is strictly greater than 1. However, we have a bit of an issue here because this forms a contradiction, because we know that the sine of any angle must be less than or equal to 1. Okay, so we just need to note this here then. So we're going to say, however, this forms a contradiction. So you do need to state this as well. So this forms a contradiction as the sine of any angle must be less than or equal to 1. Okay. So therefore, this proves then the original statement here. So therefore, sine theta plus cos theta is less than or equal to root 2. Okay. And now we have it proof complete, and that gives us the solution there to question 5. Moving on to question 6 now, where we have figure 1, which shows part of the graph of equation y equals f of x, where f of x equals the modulus of 2x plus 1 minus 5, where x belongs to the reals. The finite region R, as shown shaded in figure 1, is bounded by the graph of equation y equals f of x and the x-axis. We're then told that the vertex of the graph is at the point P. So we can see that here on our diagram. So this point here, P. So for the first part then, part A, we just want to find the coordinates of P. So only 2 marks for this, so we shouldn't expect too much work here. So for part A then, for the vertex at P, we're looking for the coordinates. So for the vertex at P, well, this is the minimum point of my curve, or my equation, I should say. So the equation y equals f of x, that is the minimum point of that graph. Okay, so when would the minimum point occur here? Well, that would be when this modulus part here, my modulus function, is equal to 0. Okay, so for this to be equal to 0, we require that 2x plus 1 equals 0. So we require that 2x plus 1 equals 0. So 2x plus 1 equals 0. If we solve this straightforward linear equation here, we get that x equals minus a half. Therefore, x equals minus a half. Okay, so that's the x coordinate. What about the y coordinate then? Well, if this part here is just equal to 0, that means that y must be equal to minus 5. Okay, in that case then, when x equals minus a half, y is equal to minus 5. Therefore, P has coordinates of minus a half and minus 5. Okay, and there we have it. So that is the solution to part A. Now for part B, it says find the area of the shaded region R, giving your answer in its simplest form. So we just go back to the diagram here. Now, when you see kind of like a shaded region like this R, and you're thinking about areas, your first thought might be integration, and that's not a bad thought, but for this question here, it's not going to work because we're working with a modulus function, okay? So what other method can we approach here to find the area of the shaded region R? Well, if we just think about this for a moment, we actually have a shape that's formed here. If we think about this point here, and then this point here, P, this forms a triangle, okay? So if we've got a triangle here, well, can we find the area of that triangle? Well, if we think about it for a moment, this is nice and straightforward because I've got a perpendicular height here from P to the base, okay, cutting through R there, the base like that. This forms a right angle. So to find the area then, nice and straightforward, it's just half times the base times by the height, okay, or the perpendicular height, I should say. So what we need then is this point here and this point here, because if we know these 2 points, we can find the distance then between those 2 points, and that distance is my base, okay? We know the perpendicular height, we've already got that because that is this distance then. So P, that was a y coordinate of minus 5, but if we think about it as a distance, that must be positive, so that's 5, okay? So the perpendicular height then is 5 units, okay? So like we said, then we need these 2 points here. So to find these 2 points here, we require that f of x is equal to 0, okay? So we need f of x equals 0 here. So f of x equals 0. So in that case then, if f of x equals 0 here, what we've got is the modulus of 2x plus 1 minus 5 equals 0. Okay. So we start here by considering the positive part to this. That would just be 2x plus 1. So we've got 2x plus 1 minus 5 equals 0. 1 minus 5 is minus 4. So add that then to the other side. So we get 2x equals 4. And therefore x equals 2. Okay, so that's my first solution. So x equals 2 there. We've also got another solution here. We'll do this to the right here. That's when we take the negative of this. So that would be minus 2x minus 1. So minus 2x minus 1 minus 5. And this all equals 0. Okay. Well, minus 1 minus 5, that's minus 6. If we add that to both sides, I get minus 2x equals 6. And now if we divide both sides by minus 2, we find that x is equal to minus 3. Okay. So I've got the points here then. So I've got positive 2 and minus 3. So if we go back to the diagram then, this must be the minus 3 here. And this must be the positive 2. Okay. So in that case, then what that means then is my distance here from minus 3 to 2, that base then has a measurement of 5 units. Okay. So from here all the way across, this is 5 units. Okay. So what I've got then is a triangle. Let's draw it out here. Not perfect, but you get the idea. We've got our perpendicular height then. This is 5 units. My base is also 5 units. So to find the area then, the area here, so that's going to be a half of the base, which is 5, times by the perpendicular height, which is also 5. So in other words, we've got 5 squared divided by 2. What we get then is 25 over 2. Okay, so if we just go back then to the actual part here where we're writing the answer or our solution, the area, like we said, is equal to a half times the base times by the height. We get a half times 5 squared, which gives us 25 over 2 there. Okay, we weren't given any units, so if you want, you can put units squared, but it doesn't matter, you wouldn't be penalized. We're not doing this. I'll just put it anyway. So 25 over 2 units squared there. That gives the area then of the shaded region R, And that gives us the solution to question 6. Moving on to question 7, then we've got f of x equals the natural logarithm of 2x minus 1 plus x squared minus 3 for x being strictly greater than a half. Now for the first part here, pretty standard stuff. We want to show that f of x equals 0 has a root alpha in this given interval here. So to show this, so for part A, what we need to consider here is a change of sign. So what I'm going to do to begin with is find f of 1.5. So f of 1.5. So to do that, we're just going to substitute 1.5 into f of x here. We're going to get the natural logarithm of 2 lots of 1.5, so that's 3, minus 1, so that's ln2, or ln2, plus 1.5 squared. And then finally, minus 3 here. And what we're hoping for is that one of these values will be negative and the other value will be positive. So just put this into your calculator here. And if you do this correctly, what you should find then is you get minus 0.05685. Okay, so we'll keep going on, but to that degree of accuracy is absolutely fine. And clearly this is less than 0. Okay, so this is less than 0, so that's negative. So what we're hoping for now is that f of 1.6, this will be positive. That's what we're hoping for. Okay, so in that case, then this would be the natural logarithm. So it's going to be 2 lots of 1.6, that's 3.2 minus 1, so that's ln 2.2 plus 1.6 squared. And then finally, minus 3. Okay, so just use your calculator again here to evaluate this. And if you do this correctly, what you should find then is we get 0.3485. So let me try and write that down again. 0.34845. And again, this will keep going on. But to that degree of accuracy, it's absolutely fine. And clearly, this is greater than 0. This is positive. Okay, so that's greater than 0. So what we've got here is a change of sign. So let's make a note of this here. So there is change of sign. And what we also need to note here is that my function of x here is continuous in this given interval here. Okay, so there is a change of sign and f of x is continuous. So continuous, hopefully I'll have enough room to fit this on. So continuous, US, is continuous in the given interval. So if we have a change of sign and our function here, f of x, is continuous in this given interval, then that tells us there is a root alpha for f of x equals 0 in this interval here. So therefore, f of x equals 0 has a root alpha in the interval of 1.5 to 1.6. Okay, and there we have it. So that is the solution to part A. Pretty standard stuff though, hopefully nothing too challenging just to get us started. And for part B then, it says find f prime of x. So just 2 marks for this. So f prime of x then. So obviously we start with f of x. If we want f prime of x, we're just differentiating f of x here. So we're going to go term by term. So nothing, that you shouldn't have seen before. So the natural logarithm of 2x minus 1. When I differentiate this here, what I'm going to get then is 2 over the argument here. So 2 over 2x minus 1, because the derivative of this is 2. So we get 2 over that. We get 2 over 2x minus 1. Then my next term here is x squared. So if we differentiate that, we get 2x. And then for the minus 3 here, well, that is a constant. Remember, when you differentiate a constant, the result will always be 0. Okay, so we just get 2x then to finish with. We get 2 over 2x minus 1 plus 2x. Okay, and there we have it. So that is the solution to part B. Nice and straightforward. Now for part C, it says using x0 equals 1.5 as a first approximation, apply the Newton-Raphson procedure once to obtain a second approximation for alpha, giving your answer to 3 decimal places. So Let's just start by stating the formula then for the Newton-Raphson procedure. Don't forget this is given in the formula, but you don't have to worry about memorizing this. We've got x of m plus 1. This is equal then to xm minus, so xn minus f of xn all over f prime of xm. Okay. Where our first term here, x naught, is equal to 1.5. So in this case here, if we want x1, that would be when n equals 0. So for us then, x1 here, that's going to be equal to x naught minus f of x naught all over f prime of x naught. Where x naught here is 1.5. So put all that together then, x1 here is going to be equal to x naught, which is 1.5, minus f of x naught. So we've actually already evaluated this. We did this in part A for the change of sign. Remember, we did that here. That was ln 2 plus 1.5 squared minus 3. So if you still got that in your calculator display, then you can use that. But let me just write it out in full here. So like we said, that's ln 2. So minus ln 2 plus 1.5 squared minus 3. And that's all over. So now it's f prime of x naught. So f prime here, or f prime of x, is 2 over 2x minus 1 plus 2x. So that's going to be 2 all over 2 lots of 1.5. So that's 3 minus 1. That's 2 over 2, so that's 1 plus 2 lots of 1.5. So what I get here then is 2 over 2, like we said. It's 2 over 2 plus 3 there. Okay, so that's 1 plus 3, giving us 4 there for the denominator. And what you need to do here is just put all this into your calculator. So you'll get 1.5 minus 0.0565. Remember, this was just what we found in part A. So that keeps going on and on and on. And this is all over 4, because 3 plus 1 is 4. So now just put this into your calculator here. And what you should find then, and what did it want it to? 3 decimal places? Yeah, 3 decimal places. So to 3 decimal places, then we get 1.514 there. Okay. And that is to 3 decimal places there. Okay. But there we have it. So that is the solution to part C. And that gives us the solution there to question 7. Moving on to question 8, then, where we're given f of x equals 1 over x, and we want to prove from first principles that the derivative, f prime of x, is equal to minus 1 over x squared. So we have a question here on differentiation from first principles, so a good place to start by just stating the result then for differentiation from first principles. So this result is given in the formula, but you don't have to worry about memorizing this here. So f prime of x, the derivative, this is equal to the limit as h tends to 0 of f of x plus h minus f of x, and this is all over h. Okay, so this is the result that we're going to use for this question here. So f of x equal to 1 over x. So what about f of x plus h? So f of x plus h, that would simply be 1 over x plus h. So 1 over x plus h there. Okay. So now we put all this together here. What we've got then is the limit as h tends to 0. So f of x plus h, that's 1 over x plus h. So 1 over x plus h there, like so. We then minus f of x, so minus 1 over x here, like so. And this is all over h. Okay, just using the result then for differentiation from first principles. And what we've got here is this expression. It's a little bit messy here. It's not very neat. So we need to clean this up a little bit. So to do that, what I'm going to do is I'm going to get the numerator here over a common denominator. So we get this over a common denominator here. We have the limit as h tends to 0. So 1 over x plus h minus 1 over x, getting this over a common denominator then, we get x minus x plus h all over x times x plus h. So putting that together then, I would say we've got x minus x plus h. This is all over x times x plus h. And then this is all over h. Okay, so this is my numerator here. This is my denominator of h. Okay, let's keep going. Now we can simplify the numerator again here. So in this case here, notice I've got x minus x plus h. So this x here will cancel with this x here. What I get left with then is minus h all over x times x plus h. Okay, so let's write that down. So we've got the limit here as h tends to 0. Like we said, then we get left with minus h. So minus h over x times x plus h. Or if we expand this, we get x squared plus xh. So x squared plus xh. And this is all over h. Okay. So from here then, what I can do now is perform the division. So we've got the limit again as h tends to 0. So limit as h tends to 0. Well, minus h over x squared plus xh divided by h, that's the same as times in by 1 over h. So write that out in full. What I've got here is minus h all over x squared plus xh times by 1 over h, like so. So here now the h's will cancel. And what I get left with then is the limit as h tends to 0 of minus 1 all over x squared plus xh. Okay. And we're nearly done then. All we need to do now is consider the limits here. So now take the limits as h tends to 0. So as h tends to 0, all that's going to happen here is this part, this xh, will tend to 0 as well. Okay. So in that case then, what we get left with here is minus 1 over x squared. So this gives us then, so let me just write here. So we'll take limit So in other words, h tends to 0, and therefore what we get then, so therefore f prime of x is equal to minus 1 over x squared as required. Okay, and there we have it. So that gets us all 6 marks there, and that gives us the solution to question 8. Moving on to question 9 then, where we have a geometric series which is given as a plus ar squared plus, and this will just keep going and going. Now for the first part here, part A, we want to prove that the sum of the first n terms of the series is given by this result here. And this is a result that you'll have used many times in A-level maths, and hopefully you may even know how to prove it already, but if not, let's just quickly demonstrate this proof. So to begin with then, for part A, all we're going to do here is consider this geometric series. We're going to call this Sn. Okay, so we've got Sn here, and that is equal then to A plus AR squared, and that would keep going and going. So we've got A plus AR squared plus AR cubed. Gets a little bit repetitive, but we keep going, right? So let's just fast forward here towards the end of this series. Now towards the end, we've got AR to the power of n minus 2. And then for my very last term here, we've got AR to the power of n minus 1. Okay. Now let's consider this series again, but now multiplying through by R. Okay. So R here multiplied by Sn. So we get RSM. Okay. And then with each term here, we multiply that by R. So my first term in this series would be A times by R, so it would be AR. The next term would be AR times R, so that's AR squared. You can see what's going to happen here. We get AR squared plus AR cubed. And again, this keeps going on and on. So let's skip forward a little bit here. So towards the end then, what are we going to get? Well, I'm going to get AR to the power of n minus 1. And then for my very last term here, we're going to get AR to the power of n. Okay, so we get AR to the power of n there. Now what I'm going to do is I'm going to call this first series here equation 1. And then the second series here, equation 2. And what I want to consider now is the difference here between equation 1 and equation 2. So I'm going to subtract equation 2 off equation 1. we're doing 1 minus 2 here, or equation 1 minus equation 2. So if we do that here, well, what I'm going to get then is Sn minus RSM. Okay, so we get Sn minus RSM. Now, in terms of the terms, if that makes sense, so I've got AR plus AR squared plus AR cubed, so on and so on. I've got AR plus AR squared plus AR cubed, and you might even spot what's going to happen here, because you think about this for a moment, I can't subtract A from this one here, because we don't have any A's within this series here, okay, or equation 2. However, we do have an AR here and an AR here, so they'll cancel. The same is true here for AR squared again, AR cubed, and you can probably see what's going to happen now. So the AR to the power of n minus 2, that would cancel with the term just before this one here, so say there, we've got AR to the power of n minus 1, and that cancels with the very last term then in this series. And what we get left with then here is this first term here, A, and my very last term here then in this series, AR to the power of n. Okay, so if we subtract those, I get A minus AR to the power of n. Okay, now we're not quite where we need to be here. If we just take a moment to look at what we want Sm equals A lots of 1 minus r to the power of n all over 1 minus r. So how do we get something that looks like that? Well, you might notice straight away that we can actually perform, or we can factorize here, both on the left-hand side and the right-hand side. On the left-hand side, we're going to factor out Sn here. We get Sn lots of 1 minus r. And that is equal then to A lots, so A lots of 1 minus r to the power of n. And we're pretty much there now. All I need to do here to finish with is just divide both sides by 1 minus r. Therefore, Sm is equal to A lots of 1 minus r to the power of n all over 1 minus r. Okay, and there we have it. Like you can see, we've got exactly what we wanted here. So A lots of 1 minus r to the power of n, perfect, all over 1 minus r. So exactly as required there. So as required. Okay, and there we have it. So that is the solution to part A. Now, if we take a look at part B then, it says find the value of x that satisfies, so we've got the sigma notation here. So I've got the series then of 2 to the power of r plus x from r equals 1 to 10, and this is equal to 2086. So where do we begin here? Well, we're not really given kind of any clues on where to begin here. So if we just think about this for a moment, what you might hopefully recognize is this 2 to the power of r. On its own, this would form a geometric series because this is just powers of 2, right? So my common ratio would be 2. My first term would also be 2. So let's just go down a little bit here. So for B then, we've got the series then from r equals 1 to 10 of 2 to the power of r plus x. And this is equal then to 2086. Okay. Like we've already said, this bit here on its own will form a geometric series. Now, x here will just be a constant. So what I can actually do then is split this up as the summation, or two individual summations, I should say. Okay, so what I've got then is the summation from r equals 1 to 10 of 2 to the power of r plus the summation of x, again, from r equals 1 to 10. Okay. Absolutely fine to split the summation up like this here. And the result will still be the exact same. Okay, so this is equal to 2086. Okay. Now, like we already noted, this here forms a geometric series. So the sum from r equals 1 to 10 is just using this result here, what we've just proved, right? So let's make a note of that here. So 2 to the power of r, this forms a geometric series. That's going to be 2 plus 4 plus 8 plus so on and so on. Okay, so in that case then, we can easily evaluate the sum of the first 10 terms using this result here. Okay, let's do that underneath here. So the summation then of 2 to the power of r from r equals 1 to 10. We now use this result here, scrolling up a little bit. We're going to use this here where a is 2, my first term is 2. My common ratio between each term would just be 2 as well. And n, that would be 10. Okay. So putting all of that together then, what are we going to get here? Well, we get 2 times 1 minus r, so that's going to be 2 as well, to the power of n, where n equals 10 here. And this is all over 1 minus r, so 1 minus 2 then. Okay. So clearly you need to use your calculator to evaluate this here. What we'll actually get is 2 lots of minus 1023. And that's all over minus 1. If we evaluate this here, then what we get is 2046. Okay. Now, what about this summation here? Okay. Well, like we said, x is just a constant. So you think about summing a constant up here. Okay. Let me just write down the sigma notation here. The series. Got the series of x here. The summation of x from I equals 1 to 10. And with x just being a constant here, what I can do is use linearity and take the x outside the summation here. So we can write this as x lots of the summation of 1 from r equals 1 to 10. And the summation of 1 from r equals 1 to 10, well, that's going to be 1 plus 1 plus 1 10 times. Okay, so this here would just be 10. So it's x times 10. So that gives me 10x, right? Okay, hopefully that makes sense. We get 10x there for the summation of x from r equals 1 to 10. So now we put all of this together, like we've done here, we split this up into 2 individual summations. So if we sum these together, then what I get here is 2046 plus the 10x here. Okay, and this then is equal to 2086. And from here now we get a nice straightforward linear equation to solve. I'm going to start by subtracting 2046 off both sides. So I get 10x is equal to 40. And then from here, we just divide both sides by 10. And we find that x is equal to 4 there. Okay. And there we have it. So just breaking it down individually, like we've done here. This bit then was just equal to 2046. The second summation, the summation of x from r equals 1 to 10, that was 10x. Putting that all together then, we just solve this straightforward linear equation to find x equals 4. Okay, but there we have it. So that gives us the solution there to question 9. If we take a look then at question 10, where for the first part, it says by using the formula for sine of a plus b and the appropriate double angle formulae, show that sine 3 theta is identical to 3 sine theta minus 4 sine cube theta. So this is a pretty standard kind of opening here to a trig exam style question. The first part involves us proving some trig identity, and then the second part involves us solving an equation that involves the use of the identity established in part A. So like we said, let's start with part A then. Now for part A, like the question says, by using the formula for sine of a plus b, so let's just start by stating this result here. So sine of a plus b. Now this result is given in the formula, but let me just zoom in a little bit here just so we can see it a bit better. So sine of a plus b, like we said, it's given in the formula book. So this is sine a cos b. So sine a cos b. Then we have plus cos a sine b. Okay. Now, what we want here is sine 3 theta. So what I can do then is replace a with 2 theta. Replace b with theta. So we've got sine of 2 theta plus theta. Obviously that would simplify to give us sine 3 theta. But what I can do now is replace the a here with 2 theta and the b's here with theta. So what we've got then is sine 2 theta cos theta. We've then got cos 2 theta multiplied by sine theta. Okay. So from here then, it's just a matter of using the appropriate double angle formulae, simplifying, and hopefully we should obtain this required result here. Okay. So in that case then, we've got sine 2 theta. So sine 2 theta, hopefully you're familiar with this result. This is 2 sine theta cos theta. Like so. So we can replace this sine 2 theta here with what I've got here on the right hand side. So what I'll do is I'll put the cos theta on the left hand side just so it looks a little bit more natural here. So cos theta times by 2 sine theta cosine theta, like so. We've now also got cos 2 theta here, so just be slightly careful with cos 2 theta, because there's a few different things that we could substitute in here for cos 2 theta. The one result that we want to use here, that is simply going to be 1 minus 2 sine squared theta. We want to use this here because notice for the actual result that we want, let me scroll up a bit, everything's in terms of sine. Okay, so there's no cosine involved here, it's just 3 sine theta minus 4 sine cubed theta. So it makes sense to keep that then in terms of just sine here. So we can replace this then. I've got plus, again, I'll write the sine theta here on the left hand side. So plus sine theta here, I've got 1 minus 2 sine squared theta. Okay, let's keep simplifying here. So what I'm going to do then is I'm going to expand these brackets. So I've got cos theta times 2 sine theta cos theta. Expanding that out gives us 2 sine theta cos squared theta, like so. We've then got sine theta times this bracket here. So sine theta times 1 is simply sine theta. So plus sine theta. Then we've got sine theta times minus 2 sine squared theta. That leaves us with minus 2 sine cubed theta. Okay. Now the next issue here is this cos squared theta. However, we know that sine squared theta plus cos squared theta is equal to 1. And what we can do then is rearrange this and make cos squared theta the subject. In that case then, cos squared theta is equal to 1 minus sine squared theta. Okay. So in that case then, replacing cos squared theta with 1 minus sine squared theta, what we get then is, let me just write it out in full again. I've got 2 sine theta times by 1 minus sine squared theta. Obviously, I can't do anything with these terms just yet, so I'll just write them out again. So sine theta and minus 2 sine cubed theta. Okay. So now if we expand this final bracket here, we've got 2 sine theta times 1. That gives me 2 sine theta. We've then got 2 sine theta times minus sine squared theta. So that gives me minus 2 sine cubed theta. Then we've still got these terms here. So plus sine theta. And then finally minus 2 sine cubed theta. Okay. Then to finish with here, we just collect like terms. Well, I've got 2 sine theta plus sine theta, so that gives me 3 sine theta there. And then finally, we've got minus 2 sine cubed theta minus another 2 sine cubed theta. So in total, we've got minus 4 sine cubed theta. Okay. And that was for sine 3 theta there, which is exactly what we wanted. So sine 3 theta is identical to 3 sine theta minus 4 sine cubed theta as required. Okay, and there we have it. So that is the solution to the first part, part A. Now for part B then, so let me just scroll up and read the question. It says, hence or otherwise for theta between 0 and pi, solve the equation 16 sine cubed theta plus 2 equals 12 sine theta. Given your answer in terms of pi. So where do we begin here? Well, let me just start by writing down the original trig equation. We've got 16 sine cubed theta plus 2, and this is equal then to 12 sine theta. Now what we're looking for here is to use this identity established in part A to help us answer part B, and this was for theta between 0 and pi. Okay, so what I want then really is something of this form here. So 3 sine theta minus 4 sine cubed theta, if we can obtain that. Okay. Well, what I notice is we have 16 sine cubed theta. I've also got 12 sine theta here. So what I'm going to do to begin with is subtract 16 sine cubed theta off both sides and see what I obtain. So if we do that then, we get 12 sine theta minus the 16 sine cubed theta there. Like so. And this is equal to 2. Okay. That's equal to 2. So what I've actually got here then is 4 lots, because I can factor 4 out here. So 4 lots of 3 sine theta minus 4 sine cubed theta. Okay. And notice this here is exactly what we've got in part A. So what I've actually got then is 4 sine 3 theta, okay, because I've got 4 lots of this here, and this here is identical to sine 3 theta. We've got 4 sine 3 theta is equal to 2. So the argument here of our trigonometric function is 3 theta. We started with the domain being for theta, so let me just adjust the domain here to account for this. So obviously we want 3 theta, we need to times through by 3. We're going to get 0 again. We get 3 theta, and now we have 3 pi. Okay, that's my new domain here. So the first thing I'm going to do then to solve this trig equation here is divide both sides by 4. So I get sine 3 theta is equal to 2 over 4, which is the same as a half there. And now that we've isolated the trigonometric function, I can now take sine inverse of both sides. So if we do that then, we get left with 3 theta. So therefore 3 theta is equal to sine inverse of a half, or arc sine of a half, whichever you prefer to write. So sine inverse of a half. Now, clearly we're working in radians here, so just ensure that your calculator is in radians mode rather than degrees mode. So put this into your calculator here, and what you should find then is we get pi over 6. So we get pi over 6 there. Now, I'm going to use a cast diagram here just to quickly illustrate the other solutions. So I'll do it up here, like so. It's not perfect, but you get the idea. So I've got C, A, S, and T. Okay. So this solution here, that corresponds to this angle here. Okay, so that is pi over 6. Now for sine here, we're working with sine. Whereas my next solution? Well, that's in this quadrant here. This S corresponds to sine. So what I've got then is this angle here. Now this angle here is the exact same. That's also pi over 6. My next solution is given by going from this line here, what would be my x-axis, going all the way around until we meet this line here. We're going to consider what the angle that is formed here. Okay, so what's this angle that's formed? Well, that would simply be pi here, it's 180 degrees, so pi minus the angle in between, so pi minus pi over 6, and what I get then is 5 pi over 6. Okay, so 5 pi over 6 there. And what we call this is the principal solutions. Okay, and from here we can now identify the remaining solutions because sine is periodic every 2 pi radians. So sine is periodic every 2 pi radians. So let's make a note of it here just in case you're not familiar with that. Okay, so let's scroll down again. So in that case then, my next solution here would be taking pi over 6 and adding 2 pi to that. So 2 pi plus pi over 6, that's the same as 12 pi over 6 plus pi over 6, that gives me 13 pi over 6. Okay, so my next solution is 13 pi over 6. For my next solution then, we go to this one here and add 2 pi again, because like we said, sine is periodic every 2 pi radians. So if I've got 5 pi over 6 and I add 2 pi to that, that's the same as 5 pi over 6 plus 12 pi over 6. That would give me 17 pi over 6. Okay, we get 17 pi over 6 there. So the next solution would be 13 pi over 6 plus 2 pi. However, the issue here is, if I add 2 pi to this, we're going to fall outside of this domain here for 3 theta. Okay, so at this point now, what I've got here is the full set of solutions for 3 theta. However, we're solving for theta. So in that case then, if we want these solutions for theta, we're going to have to divide each solution here by 3. Okay, so let me just write this out here. So 3 theta is equal to pi over 6, 5 pi over 6, 13 pi over 6, and then finally 17 pi over 6. And like we said, we just want theta here. So in that case, I'm going to divide through by 3 here. So theta, going from 3 theta to theta, we divide by 3. And we do the same here with these angles, okay, or these solutions here, I should say. So in that case then, pi over 6 divided by 3, it's the same as timesing through by 1 over 3. So pi over 6 times by 1 over 3, that gives me pi over 18. So we get pi over 18 there. We've got 5 pi over 6. This would just be 5 pi over 18. So basically just change all the denominators now to be 18. So 5 pi over 18 we've got 13 pi over 18. And then finally, 17 pi over 18. Okay. And there we have it. So these 4 solutions here is the full set of solutions for theta. And there we have it. So that gives us the solution there to question 10. Moving on to question 11 then, where we have the curve C, which has the following equation. So we've got x equals sec squared y minus 4 tan y. Now for the first part here, we just want to verify that the point P with these given coordinates of -2 and pi over 4 lies on C. So nice and straightforward here just to get us started. So for A then, let me just go down a little bit here. So to show that this lies on the curve C, don't forget the equation we're given is x equals sec squared y. Got sec squared y minus 4 tan y. And the point we had for P was -2 and pi over 4. So if P here lies on this curve here, C, then when I substitute this point here into the curve, or the equation I should say, the equation should hold. Okay, so the left-hand side should be equal to the right-hand side for this given point here. So in that case then, let's replace y here with pi over 4, and hopefully we should find that the left-hand side here then is equal to -2. I've got sec squared pi over 4. So sec squared pi over 4 minus 4 lots of tan pi over 4, like so. Well, sec squared pi over 4, that's equal to 2. Tan pi over 4 is equal to 1. So -4 tan pi over 4, that's minus 4 lots of 1, so that's -4. And 2 minus 4 is equal to -2 as required there. Okay, so as required. And that proves then that the point P lies on the curve C. So therefore, P with coordinates -2 and pi over 4 lies on C. Okay. And there we have it. So that's the solution to part A. Hopefully nice and straightforward. So for part B then, it says show that dy by dx is equal to cos squared y over 2 tan y minus 4. So notice here we start with the equation as x equals sec squared y minus 4 tan y. What we need to do here is start by differentiating x with respect to y, so we're going to get dx by dy, and then we'll take the reciprocal of that, and hopefully we should end up with this here. Okay, so for B then, let's start here. So x equal to sec squared y minus 4 tan y. So we're looking for dx by dy. So dx by dy, let me zoom in a little bit here. So dx by dy then. So we're going to go term by term here. So I've got sec squared y. So obviously this requires the use of the chain rule. So what I'm going to get here then is 2 sec y. And then we times this by sec y tan y. So sec y tan y there. Like so. So that's my first term complete. We then got minus 4 tan y. So nice and straightforward here. If we differentiate this, we're going to get minus 4 sec squared y. So minus 4 sec squared y there. Okay. And then from here, it's just a matter of simplifying this. So I'm going to start by expanding this. So I've got 2 lots of sec squared y. So 2 sec squared y tan y minus 4 sec squared y. Okay. From here, then we can now factor out a 2 sec squared y. We've got 2 sec squared y. So then we're going to get a bracket here. We're going to get tan y minus 2 here. We get tan y minus 2, like so. And obviously, we're looking to get it into this form here. Okay, so we're going to need a bit of work here from this point here. So given that we've got sec squared y here, and obviously I can see the numerator here involves cos squared y, and rather than writing it like this here, we're going to write it as the reciprocal trig function itself. So it's going to be 2 over, so this is 2 over cos squared y times by tan y minus 2. And you don't need to write obviously this step out here. I just want to make it clear what we're going to actually do here. So what I get then is 2 lots of tan y minus 2. 2 lots of tan y like so. And that is over cos squared y. Okay. And we're nearly there now. Obviously, I can expand here, this bracket here with this term on the outside. We'll do that here on the next page. We get 2 tan y minus 4 all over cos squared y. And remember, this is for dx by dy. So this is dx by dy. But remember, we want dy by dx. Okay. And notice here now, dy by dx is just the reciprocal of what we have here. Okay. So now, in that case, then, dy by dx will simply be given then as the reciprocal of this. We get cos squared y all over 2 tan y minus 4 there. 2 tan y minus 4 as required. Okay. And there we have it. So that is the solution to part B. Like you can see, we've got the exact same as what we required here. So that's part B done. And then finally for part C, it says, show that the equation of the tangent to the curve C at the point P can be expressed as 4y minus pi is equal to minus x plus 2. So let's go down then. So for part C here then, looking for the equation of the tangent to the curve C at the point P. So the first thing that we need here is the gradient at the point P. So we need the gradient at P, which has coordinates of minus 2 and pi over 4. Okay. So we've got dy by dx here. So dy by dx then. This is going to be equal then to cos squared pi over 4. So cos squared pi over 4. Put it in brackets just to make it clear. Cos squared pi over 4. Then this is all over 2 lots of tan pi over 4. And then we've got minus 4 here. So now we just need to evaluate this on our calculator. Well, cos squared pi over 4, that is equal to a half. So we've got a half divided by, well, tan pi over 4, that's 1. So this is 2 lots of 1 minus 4. So I get 2 minus 4 there, giving me minus 2. Well, a half divided by minus 2, that is equal to minus 1 over 4. Okay, minus a quarter there. So now we've got the gradient here, we've got the point. So we've got everything that we need then. So now we're just going to use, here y minus y1 is equal to m, the gradient, times x minus x1. Okay, close that bracket. So now, don't forget x1 here is minus 2 and y1 is pi over 4. So in that case, then we get y minus pi over 4 is equal to m here. Now, m in this case will just be minus 1 over 4. We want the equation of the tangent rather than the normal, so we don't take the negative reciprocal here. If we wanted the equation of the normal, then you would take the negative reciprocal of this. So it would then be 4. But in this case, just because we want the equation of the tangent, we just keep it as minus 1 over 4. So it's going to be minus 1 over 4 times x minus x1, which is minus 2. So minus 2, this becomes plus 2. Just be very careful for that. Like so. Now, because I want it in this form here, so let me just go back up. I want it in this form here. 4y minus pi is equal to minus x plus 2. So rather than having this as a fraction here, say pi over 4, I'm just going to start by timesing through by 4 here. Okay. So I get rid of this fraction here as well. I'm going to get 4y minus pi is equal to minus bracket x plus 2. Okay. And was that the form we wanted? Let's just double check here. So 4y minus pi is equal to minus x plus 2. Perfect. Exactly as we needed there. So as required. And there we have it. So as required there. Exactly as we needed. Okay. And there we have it. So that gives us the solution there to question 11. Moving on to question 12 now, where it asks us to show that the integral of 3x multiplied by the square root of x plus 2 with respect to x from 0 to 2 is equal to 16 over 5 multiplied by 2 plus root 2. Now, for this integral here, it doesn't tell us what method we need to use. It doesn't say, for example, use integration by parts. It doesn't give us a substitution to use. We're just left to our own devices here. So it's up to you which method you choose to approach this integral with. For this question here, question 12, I'm going to use integration by substitution. However, if you've already noted that you could use integration by parts and you prefer integration by parts, that's absolutely fine. I do think integration by substitution is a little bit easier for this integral. But like I said, integration by parts is absolutely fine as long as you can get the result here. Okay, so where do we begin? Well, we need to choose a substitution here. And for me, I think the easiest substitution here is u equals x plus 2. So I'm going to start by letting u equal x plus 2. So we let u equal x plus 2 here. Now, whenever we're given our substitution here, or we denote our own substitution, the first thing that we need to do is find du by dx. So we're going to find du by dx here. So du by dx then. But what would du by dx be here? Well, that would simply be 1. And therefore, if du by dx is equal to 1, what that tells us then is du is equal to dx. Okay. So that's helpful because we can now replace the x here with du. Okay. What else do we need? Well, we need 3x here because we've already got the substitution then for the square root of x plus 2 because u is equal to x plus 2. So that's the square root of u. We've got dx, that's equal to du. But what about 3x then? Well, what I need to do then is rearrange this and make x the subject. So if we do that here, x is equal to u minus 2, like so. And because we've got 3x here, we need to times this by 3. So therefore, 3x is equal to 3u minus 6. Okay. And it might seem like we're doing quite a bit of work here just to get started, but it is important that we kind of lay out all the foundations before we begin with this integral. So we've got everything that we need here now. So let's transform this integral here then. So we've got the integral then of 3x. Let me write down the original integral. So we've got 3x multiplied by the square root of x plus 2 with respect to x from 0 to 2. Okay. Now, I'll come back to the limits in a moment. We'll transform those in a second. But for now, 3x, like we've already noted here, that's 3u minus 6. We've got 3u minus 6 there. We've then got the square root of x plus 2. Well, u is equal to x plus 2, so this is the square root of u, or in other words, u to the power of a half. We times it by u to the power of a half. And then we've got dx here, which is equal to du. Okay. Now we do need the new limits here. So how do we obtain the new limits? Well, let me do this underneath. In fact, let me do it at the top here. So the new limits, how do we obtain those? Well, it comes back to the original substitution here. U equals x plus 2. So x equal to 0 and x equal to 2. So when x equals 0, u is equal to 0 plus 2. So u is equal to 2. When x equals 2, then u is equal to 2 plus 2. So u is equal to 4. Okay. So my new limits now are from 2 to 4. Okay. So now we need to deal with the integrand here. We need to simplify this a little bit here. So if we got 3u minus 6 times by u to the power of a half, we can just multiply through here. So let's rewrite this then. We've got the integral here from 2 to 4. Well, 3u times u to the power of a half. This is 3u to the power of 1. Okay, we don't write, but there's a little 1 there. If we times these together, that's 1 plus a half. That's going to be 3u to the power of 3 over 2. So we get 3u to the power of 3 over 2. We then got minus 6 times u to the power of a half. So that's minus 6u to the power of a half. Okay. And this is all with respect to u here. So du. Okay. So from here now, what we need to do is actually perform the integration then. So what I'm going to get here then Well, if I add 1 to the power, so I've got 3u. Now add 1 to the power, so if this power here is 3 over 2, adding 1 is the same as 2 over 2, so I get 3u to the power of 5 over 2, and then we divide by the new power. So in total what we've got here is 3u, power of 5 over 2, and then we divide by 5 over 2 here. Doing the same now with this here, this term, so minus 6u to the power of a half, adding 1, again it's the same as 2 over 2, get minus 6u, power of 3 over 2, and again we divide by this new power here. So we divide by 3 over 2, like so, and our limits are from 2 to 4, and we can simplify this here then. So if we've got 3u to the power of 5 over 2, and we divide by 5 over 2, that's the same as timesing by 2 with the numerator here, because that's my denominator here. So 3 times 2 is 6. What I get then is 6u over 5, and that's the power of 5 over 2. Okay. Then repeat this here with this term. So we've got 6, we times that by 2, so that's 12. Divide that by 3, and we get 4. So minus 4u. So minus 4u there to the power of 3 over 2. Okay. Now our limits don't change, so from 2 to 4. So let's keep going here. So what we need to do now is just deal with the limits here. So we now start by substituting in the upper limit here. So in that case then, I get 6 lots of 4 to the power of 5 over 2. So here we're taking the square root of 4, so that's 2. What I've got here then is 6. Like we said, that's the square root of 4, which is 2. We then raise that to the power of 5. So 2 to the power of 5 is 32. So 6 times 32. Divide that by 5. Then we've got minus 4. So u, again, that's 4. So 4 to the power of 3 over 2. So I'm kind of doing this kind of in my head here. If you find it easier, just do jot this down as you go. So 4 to the power of 3 over 2. So again, we're taking the square root of 4 here. So that's 2. 2 cubed is 8. And then we times that by 4, that would be minus 32 there. Okay, so minus 32. So that's the upper limit then. We now just repeat this here with the lower limit, which isn't quite as easy to work with. So now we minus here. I've got 6 lots of 2 to the power of 5 over 2. So obviously what I'm going to do here is the square root of 2, which obviously it's not quite as straightforward as what we had here for the upper limit. So I've got 6 lots here. So the square root of 2, we then raise that to the power of 5. So root 2 squared is 2. We then do that again. So let me just do it over to the side here just so you can see what I'm doing. So root 2, power of 5. So that's root 2 times root 2, which is 2. Then repeat that again. That would take me to the power of 4. So that's 2 times 2, which is 4. And we times that by root 2. So I get 4 root 2 there. Okay, so I've got 6 lots of 4 root 2. Obviously, you could just do this on your calculator. I am just doing it kind of off the top of my head. Then we divide that by 5. So we divide that by 5. Then we've got minus here. So 4 lots of 2 to the power of 3 over 2. For the square root of 2 again, we then cube that. So that's 2. And we times that by root 2. So that's minus 4 lots of 2 root 2. Okay. So let's keep going here and simplifying. What have we got now? So 6 times 32, that's 192. So that's 192 over 5 minus 32. Okay, I'm simplifying as I go here. I've got 6 lots of 4 root 2, so that's 24 root 2 over 5. So minus 24 root 2 over 5 minus 8 root 2. Minus 8 root 2 there. I might be doing this in a slightly long way. It doesn't really matter. We should get to the final solution. So 192 over 5 minus 32. So again, you could just put this into your calculator here. So 192 over 5 minus 32. That's the same as 192 over 5 minus 160 over 5. That gives me 32 over 5 there. We get 32 over 5. Dealing with this bit here then. This is the same as 24 root 2 over 5 minus 40 root 2 over 5. So that gives me minus 16 root 2 over 5. Like so. So from here then, this is the same now as 32 over 5 plus 16 root 2 over 5. So plus 16 root 2 over 5. And now I can see straight away how this is going to lead to our solution. I'm going to factor out here. The 1 over 5 to begin with here. I factor out 1 over 5. We've got 32 plus 16 root 2, like so. Obviously, we want 16 over 5 here. So obviously, you could have just done it all in one swoop here. You could have just factored out 16 over 5. I've kind of broken it down into 2 steps just so you can see how that works. So then if we factor out the 16 here, we get 16 over 5. So this would be 2 plus root 2 then. Okay, which is exactly what we needed here. So as required then. So as required. And that gets us all 7 marks there. Okay, so like you can see, there's a bit of work involved with that. We're not really showing kind of, where we're starting with it. But these types of questions are quite common, so just make sure you're familiar with these types of integrals and where to begin. But there we have it. So that is the solution there to question 12. If we take a look now at question 13, where for the first part of this question, part A, all we want to do is express this algebraic fraction here in partial fraction form. So let's scroll down a little bit here. So for part A then, we have the algebraic fraction of 1 over h minus 1 and h plus 3 then. Okay, so if we split this up into partial fractions, we're going to get a over my first factor of h minus 1 plus b over my second factor here of h plus 3. Okay, so what we need to do then is get this right hand side here over a common denominator. This would be a lots of h plus 3 plus b lots of h minus 1. Okay. And now what we've done here is we've got this over a common denominator. I've not written the denominator here, but my denominator would be h minus 1 times h plus 3, which is the same as the left-hand side here. So what that means then is my numerators here must be identical. So this is identical then to 1. So all I'm going to do now is substitute values of h in to eliminate both a and b. So for example, if we let h equal, say, 1 here, if we let h equal 1, I get 1 minus 1, which is 0. B times 0 is 0. And from there, we can go on to solve for a. So in that case, then we get 1 plus 3, which is 4. We get 4a is equal to 1. And then if we divide by this coefficient here of 4, we find that a is equal to a quarter. Okay, 1 over 4 there. And then we repeat this again here to find out the value of b. If we let h equal, say, minus 3 here, then what do we get? Well, I get this bit here would be 0. Minus 3 plus 3 is 0. So a times 0 is 0. We then get minus 3 minus 1, which is minus 4. So I get minus 4b is equal to 1. And therefore, if we divide by the coefficient again of minus 4, we find that b is equal to minus 1 over 4. Okay. We're pretty much done now. Let's just write down the actual partial fraction decomposition. So in that case then, we had 1 over h minus 1 and h plus 3. So splitting this up then into partial fractions like we found here. Well, a is 1 over 4. So I'm going to write this as 1 over 4 lots of h minus 1, like so. And we've got minus 1 over 4 here, so that's minus 1 all over 4 lots of h plus 3 there. Okay. And there we have it. So that is the solution to the very first part there, just the partial fraction decomposition. That gets us the first 3 marks. Now, for the second part here, like you can see, it's 9 marks. There's quite a lot of work involved for this part of the question. Let's just take it step by step because there is a lot to take in. So we're told that the depth of water in a tank is being monitored. The depth of water in the tank, h meters, is given, or modelled, I should say, by this differential equation. T is the time in days since the monitoring began. And then we're told that the initial depth of water in the tank is 9 meters. So we want to solve the differential equation to show that h is equal to this here. So where do we begin? Well, let's just start with the differential equation. Now, if I actually take a look at the differential equation, just hopefully you notice straight away, I've got h minus 1 here and h plus 3 as a product, and we had that here as our denominator. So hopefully our answer in part A will help us answer part B. Okay. So for part B then, like I said, we're going to start with the differential equations. We've got dh by dt. So dh by dt. So this is minus, we've got h minus 1 times h plus 3. And this is all over 32. Okay. Now, obviously, we want to solve this differential equation here. So what I need to do then to solve this differential equation is separate the variables. Now, if we take a look at the left-hand side here at my derivative, dh is the numerator. So what that means then is anything in terms of h we want on the left-hand side, anything in terms of t, we want that on the right-hand side. So the first thing that I need to do then is divide both sides by h minus 1 times by h plus 3. So I'm going to divide by the product here in my numerator, which if you notice will give me what we started with, 1 over h minus 1 times h plus 3. So that's on the left-hand side. So I've got 1 over, we've got h minus 1, h plus 3. And like we said, anything on the left-hand side needs to be in terms of h. So that would be for dh there. We can't do anything further with the left-hand side. And this is equal then to minus 1 over 32. And like we said, then the right-hand side is in terms of t, so that's for dt. Okay, nothing further that we can do with the right-hand side there. So what we've done there is we have separated the variables, and now once we separate the variables, we now integrate both sides. We're going to integrate both sides here, like so. Okay, so this side here is a little bit more complicated, clearly compared to this integral here, but notice I've got 1 over h minus 1 times h plus 3. And we've already split this into partial fractions. Okay, that's 1 over 4 lots of h minus 1 minus 1 over 4 lots of h plus 3. So the very first thing that I can do here is factor out a 1 over 4 outside the integral using linearity. We can write that as 1 over 4 lots of my integral here. And then we have our partial fraction decomposition. So that's 1 over h minus 1 minus 1 over h plus 3. Like so, and that is for dh there with respect to h. And that is equal then to the integral here of minus 1 over 32. If you want to, you can factor out the minus 1 here essentially using linearity. So it'd be the integral of 1 over 32, and we'd have the minus here outside. I don't think it's really necessary, but if you find that a little bit easier, that's absolutely fine. But I'll keep it as it is. The integral of minus 1 over 32 dt there. Okay, let's scroll down. So let's keep going with this. Now, this integral here, a little bit more complicated, but nothing too challenging. Just notice the derivatives here of my denominators is the exact same as my numerator. So what I'm going to get then is a quarter of the natural logarithm then of h minus 1. Same again here, this would be minus 1 over 4 of the natural logarithm of h plus 3, because the derivative then of my denominator is the exact same as the numerator. Get ln h plus 3. And that is equal then, well, the integral of minus 1 over 32 with respect to t, that's minus t over 32. Nice and straightforward. And don't forget the constant of integration here, so plus c. Okay. So let's keep going here. Now, we need to solve and find the value of c here. So we do need our boundary conditions here. So we go back to the question. We're told that the initial depth of water in the tank is 9 meters. So when t equals 0, h is equal to 9. Let's just note that here. So when t equals 0, h is equal to 9. Okay. So in that case, then I'm going to get 1 over 4 ln. So this is 9 minus 1, so that's ln 8. Minus 1 over 4 ln, so that's 9 plus 3, so that's 12. That's equal then, well, this would be 0, because minus 0 over 32 is just 0. So that's equal to c. And then what I can do is write this as a single logarithm if I want to. So therefore, c is equal to 1 over 4 ln 2 over 3. Okay, because I've got a quarter ln 8 minus a quarter ln 12. That's the same as a quarter ln 8 over 12. Well, 8 over 12 is 2 over 3. Okay, so we find the value of c then. So now I can go back to this line here. Now what I'm actually going to do here is times through by the 32 as well, just to get rid of this fraction and include c. Okay, so if we do that here, I get a ln h minus 1 minus 8 ln h plus 3. That's equal then to minus t plus c. Well, c is a quarter ln 2 over 3, so that's also going to be 8 ln 2 over 3. So plus 8 ln 2 over 3 there. Okay. So we're getting closer to the solution here, but there is still quite a bit of work involved. Like I said, this part of the question is certainly tricky. So what I want to do now is write this as a single logarithm. So to do that, I'm going to subtract this here off both sides. Okay. So I get that minus t is equal, so I'd have 8 ln h minus 1 minus 8 ln h plus 3. And then we'd be subtracting this as well. Now, before I subtract this, let me write this as 8 ln. Then we'd have, let me do it in a bracket here. I'll leave a bit of room just so I can include it in a moment. We'd have h minus 1 over h plus 3. Like so. Okay. Now we're subtracting this as well. So in that case then, because I'm also subtracting this here, I've also factored out the 8 here. So I've already done that. I've dealt with that 8 here. Now, if we subtract ln 2 over 3, it's the same as dividing here, like we've got this quotient, but I don't want to divide this here. So I'm going to do basically the inverse of that. So, oh, sorry, not the inverse, but rather than divide it then, I'm going to times it by its reciprocal. It's the same thing, right? Okay. So obviously if you've got 1, you divide it by, say, a half. It's the same as doing 1 times 2. Okay. I'm going to do that here then. So I'm going to write this now as 3 over 2. So I'm timesing it now by 3 over 2 rather than dividing it by the 2 over 3. Okay. Same thing, but I think it makes it a little bit easier to work with. So this is minus t equals 8 ln 3 over 2 times the modulus here of h minus 1 over h plus 3. We're getting there. Let's keep going. So what I want to do now is get this as a power. Okay, so obviously we're looking to solve for h here. So I need this as a power. And we need to get rid of the natural logarithm here on the right-hand side. So to do that, we take the exponential function of both sides. So this 8 here, we can use the power law and we could write that as a power. But I don't want it as a power. So to do that, what I'm going to do then is take the inverse of that. So for example, if you square something, the inverse of that is taking the square root. So I've got the 8th power. I'm going to take the 8th root of both sides. So it's getting a little bit convoluted. So let me just kind of explain this over here. So we take the exponential function of both sides. So that would be e. So this would be to the power of minus t. Now, I'm going to leave a little bit of a gap here because I want to include something else with that in a second. That would then be e to the power of 8 ln. I'll do it over here. Just this is like my scrapbooking over here. So that's e power of 8 ln 3 over 2. The modulus of h minus 1 over h plus 3. Lost my train of thought then. So let's keep going. I'm now going to write this as a power here. I write that as a power. And now rather than writing that as a power, obviously these will cancel as well. So I'm going to get left with this here. 3 over 2 as the modulus of h minus 1 over h plus 3. Like so, and that's all to the power of 8. But rather than writing that as the power of 8, I'm going to take the inverse of that. So I'm going to take the 8th root of both sides. So if I do that here, this power now becomes e to the power of minus t over 8, or minus, like we've got here. Let me see if I've got it. Yeah, there we go. E to the power of minus 0.125t. Yeah, that's the same as 1 over 8. So that's minus 0.125t there. And that's equal then to ln, or 3 over 2, I should say. 3 over 2, h minus 1 over h plus 3. Okay, obviously we don't need the modulus anymore because we don't have the natural logarithm. So now I'm going to get rid of this 2 here because we've got 3 over 2. Well, I guess what I could just do is divide by this actually. Rather than get rid of the 2 here, I'll just divide by the full thing. So if I divide both sides by 3 over 2, I've got e to the power of minus 0.125t divided by 3 over 2. It's the same as 2e. So 2e to the power of minus 0.125t all over 3. And that is equal then to h minus 1 over h plus 3. Let's keep going. This is painful, this question. So now what I'm going to do is I'm now going to times 3 by the 3 here, which begs the question of why I divided by 3 over 2, but it doesn't really matter. We'll just keep going. I'm doing this in a bit of a sloppy way, but just keep going. I've got 2e to the power of minus 0.125t. That is equal then to 3 lots of h minus 1 over h plus 3. That would be 3h minus 3 all over h plus 3. We're getting pretty close now. Obviously, we want to solve for h here. So I've got a h here in the numerator, 3h. I've got a h here in the denominator. So we need to group these on one side. So I'm going to times 3 by h plus 3 here. So I get 2e, or h plus 3, times 2e to the power of minus 0.125t. That is equal to 3h minus 3. Then if I expand this out, what do I get? I get 2he to the power of minus 0.125t plus 6e. So 6e to the power of minus 0.125t, and that is equal to 3h minus 3. Let's keep going. We're nearly there now. So, like I said, we want the h on one side. So do they keep the 6h or the 6e as positive? Let me just double check. So that is positive. So what I'll do then is I will subtract that this here onto that side. Okay, so I've got 3h minus 2he power minus 0.125t. And that is equal then to 6e power minus 0.125t plus 3, like so. Now we can factor out the h here. We get h lots of 3 minus 2e to the power of minus 0.125t. That is equal to 6e power of minus 0.125t plus 3. There we go, we're pretty much there now. And then finally, divide through here by this factor. So therefore, let me do it underneath with a bit more room. H is equal to 6e to the power of minus 0.125t plus 3 all over. So this is all over 3 minus 2e power of minus 0.125t there. Okay, I think it looks slightly different to how they presented the solution. So yeah, it's 3 plus, but it doesn't matter. It's the exact same thing. If it makes it look a little bit neater, let me just write that the same way. So 3 plus 6e. We've done all that work, we might as well write it in the exact same way. So minus 0.125t all over 3 minus 2e power minus 0.125t there. Okay, and there we go. That was painful, but we got there. So like you can see, quite a lot of work involved for part B. Probably the trickiest part of this exam paper, but hopefully you got there as well. I hope that makes sense. So that's the solution to part B. And then finally, for part C, it says the depth of water in the tank will eventually fall to d meters, state the value of d. Now, this is only 1 mark. There's not really much work involved with this. So how do we do part C then? Well, for part C then, we're looking at what we call the limiting value here. So the limiting value. So in other words, we're going to take the limit here as t tends to infinity. So the limit as t tends to infinity. Okay. So not 0, infinity. So what would happen then to this expression here for h as t gets bigger and bigger and bigger? Well, in this case here, this part, well, that would just be 6e to a very, very large negative number. Okay, so this would just tend to 0, this bit here. So 6e to the power of a very large negative number, that would just tend to 0. The same is true here because the e is to the same power. So this bit here would also tend to 0. So in other words, this bit here will just disappear. And this bit here will also disappear. So what I get left with then for h, so this gives us this gives h equals 3 over 3. Because this bit here will disappear, this bit here will disappear. So we get left with h equals 3 over 3, which is equal to 1. So we get left with 1 meter there eventually in the tank. Okay. And there we have it. So that's what we call the limiting value. Only 1 mark for it, so not too much to worry about, just if you can't remember something like that. But yeah, we're just considering what happens as the limit for t tends to infinity. Like I said, this bit will disappear. This becomes 0, or it tends to 0. Same is true here. This tends to 0. We get left with h equals 3 over 3, giving us 1 meter there. Okay. But there we have it. So that is the solution there to, what question are we on? Question 13. Okay. So let's take a look then at the very last question, question 14. Moving on to the very last question, now we have question 14. So for the first part here, part A, all I want to do is express 4 cos x minus 3 sin x in the form r cos of x plus alpha, where r is strictly greater than 0 and alpha is between 0 and pi over 2. So let's start then with part A. Now for part A, we have 4 cos x minus 3 sin x. We want to show that this can be expressed then in the form r cos of x plus alpha. Okay. Well, to begin with here, it's nice and straightforward to evaluate r here. This is simply an application of Pythagoras. So r here is equal. So this is the square root. So we have 4 squared plus minus 3 squared. So 4 squared plus minus 3 squared, that would give us 16 plus 9. This is equal to the square root then of 16 plus 9, which is equal to the square root of 25, which would simply give us 5 there. Okay, so the value of r is equal to 5. And then for alpha here, again, nice and straightforward to evaluate here. Alpha is equal to tan inverse or arctan, whichever you prefer. So tan inverse here, in this case, of 3 over 4. So tan inverse of 3 over 4. Put this into your calculator. Now, obviously, just to ensure that your calculator is in radians mode rather than degrees mode. It's a really easy mistake to make that you've got it in the wrong setting, especially in an exam type condition. So, like I said, just make sure you're in radians here. If you do this correctly, what you should find then for tan inverse of 3 over 4 is you get 0.644. Okay, that's 0.644 radians there. And that is to 3 decimal places. Okay, so if we just write out like this again then, we had 4 cos x minus 3 sin x is identical then. So we've got r cos, well r is 5, so we've got 5 cos. Let me scroll down a little bit here. So 5 cos, and then we've got x plus alpha, so x plus 0.644. 0.644 there. And there we have it. So that is the solution there to part A. Now for part B then, just scroll back up here. We've got a little bit of information. So we're told that the height of seawater, h meters on a particular day, can be modelled by the equations. We've got this equation here, where t represents the number of hours since midday. For part B then, it says find the times at which the model predicts that the height of the seawater will be 6 meters. So, let me just start by writing down the equation here to begin with. Part B then, we had h equals, it was 5 plus 2 cos. So we had 4 pi t over 25. Let me just double check that is correct. Make sure I've got the argument correct here. So 4 pi t over 25, perfect. We had then minus 1.5 sine of 4 pi t over 25. So again, the argument's the same here. Like so. So this is the equation that we're using for part B. Now, if we're looking for the times at which the model predicts that the height of the seawater will be 6 meters, what this is saying then is h equals 6. Okay. So in that case then, I'm just going to replace h with 6 here. So we've got 5 plus 2 cos of 4 pi t over 25 minus 1.5 sine of 4 pi t over 25, and this is equal then to 6. Okay, and all I want to do here now is solve this trig equation. So to begin with, I'm going to get rid of this 5 here on the left hand side. So to do that, we subtract 5 off both sides. So let me just scroll down here and do it underneath. So I'm going to get 2 cos of 4 pi t over 25 minus 1.5 sine, again, of 4 pi t over 25. And that is equal then to 6 minus 5, giving us 1 there. Okay. Now, in its current form like this, trying to solve this trig equation, not particularly easy. Okay. However, if we go back to part A, we had something pretty similar, right? We had 4 cos x minus 3 sin x, and we expressed it in this form here. Now notice what I've got then is 2 cos of my argument minus 1.5 sine of my argument here. So ignore the argument for now. Just notice I've got 2 cos and minus 1.5 sine. Originally we had 4 cos x and minus 3 sin x. So I'm working with a half of what we started with in part A. So basically, I can express it in this form here. All I need to do is divide it by 2. So we're going to get r over 2 cos of our argument here plus 0.644. Okay. So let's do that here then. So like we said, we get 5 over 2 because it's r divided by 2 here because it's a half of what we have in part A. We've then got cos of the argument here. So that's 4 pi t over 25 plus alpha here, which is 0.644. Okay, and this is all equal to 1. So what we need to do now is divide both sides by this coefficient here of 5 over 2. On the left hand side, we get left with cos of the argument here. So 4 pi t over 25 plus 0.644. And that is equal then to 1 divided by 5 over 2. That's the same as taking 1 and timesing it by 2 over 5. So we get 2 over 5 there. Okay. Now, our trigonometric function here, cosine, is isolated, so we can go straight into taking cos inverse of both sides. So I take cos inverse here at the left-hand side, we get left with the argument here, the trig function. I get 4 pi t over 25 plus 0.644 is equal then to cos inverse of the right-hand side, which is 2 over 5. Okay. So obviously, we need to put this now into our calculator here. Again, obviously, just to ensure that you're working in radians rather than degrees. So I get 4 pi t over 25 plus 0.644. And this is equal now. So again, just put this into your calculator here. If you do this correctly, what you should find then is we get 1.1593. Okay. So let me just quickly draw a cast diagram here just to help us answer this question. I've got C, A, S, and T. Okay. So this solution here that we just found, that is within this quadrant here. Okay. So this angle is this value here. So 1.1593. Okay. That's what we just found there. Now my next solution here using our cast diagram, that occurs in this quadrant here. Okay, this angle again is 1.1593. However, the angle that we're looking for is starting from this line here and going all the way around until we meet this line again. Okay. Well, to find that, that would simply be 2 pi radians minus the angle in between, which is 1.1593. So again, put this into your calculator here. So we do 2 pi minus this value here. And if you do this correctly, what you should find then is we get 5.1239. Okay, so 5.1239 there. Now, we're looking for these solutions here for t, but just notice the condition we had for t here was that t is between 0 and 12. So obviously, we need to do a little bit of work here. This isn't the solutions because we've also got to deal with 4 pi t over 25 plus 0.644. We're actually looking to solve for t here. So it's not even in the correct form. But when I think about this here for a moment, my next set of solutions here obviously would come by taking this here, adding 2 pi radians because cosine is periodic every 2 pi radians. From there, we'd subtract 0.644, and then multiply that by 25, and we divide by 4 pi. Now, this is just kind of something that comes with experience and practice. I'm going to predict straight away that my next solution here will fall outside of the domain for t. Okay, this condition we have for t here. Okay, I'm predicting basically that this is going to be greater than 12. Now, it's up to you. You can do it, and I would definitely do at least one just to verify that that is the fact. So what I do then is I take this value here, add 2 pi radians to that, and then I'd go through with the working here. Now, I won't do it straight away, but feel free to verify that yourself. I can tell you now, it will definitely fall outside of the domain. Okay, so let's go ahead now with solving for t here. So these two values here are for this here. So what I need to do straight away is subtract 0.644 off both of these. We get 4 pi t over 25 is equal then, so 1.1593 minus 0.644. What that gives me then is 0.5153. So that's this one here. We now do the same with 5.1239. And that gives me 4.6. So 4.6106. Okay. What I need to do now is times by 25 and divide by 4 pi. Okay. I won't do it at each stage. What I'm going to do now is go straight into my solution here for t. So obviously, like I said, just times both of these by 25, divide by 4 pi, and hopefully you're going to get the same as me here. So what you should find then for t here is we get 1.02516. So 1.02516. I would keep going on and on and on for now, but I'll just leave it as this degree of accuracy here. So that's this one here, or that corresponds to this solution here, I should say. And then corresponding to this solution here, we times that by 25, divide it by 4 pi, and what you should get then is 9.17249. And again, this keeps going on and on, but we'll leave it like that for now. So obviously, like I said, if you were to verify this here, take 0.5153, add 2 pi to that, times it by 25 and divide it by 4 pi, and you'll find you get a value of t here greater than 12. Okay, so these are the only solutions here. Now we need to be slightly careful. We don't leave the answer like this. So remember, t corresponds to the number of hours since midday. So I've got these two values of t here. What I need to do now is convert this into an actual time. Okay, so this here, this 1.02516, I need to convert this to hours and minutes. Okay, so in that case then, I'm going to take 0.02516, 0.02516, times that by 60. Okay, and what this will tell me then is how many minutes this corresponds to. Okay, so in that case then, if I round this to the nearest minute, I think that's what the question asks for. It should ask for it anyway. It should ask for it to the nearest minute. I will change that on the actual paper. The nearest minute. So to the nearest minute then, what you should get here is 2 minutes. This corresponds to 2 minutes. In that case then, 1.02516, this corresponds to 1 hour and 2 minutes. So 1 hour and 2 minutes. Then we're going to repeat this here for 9.17249. So 0.17249. We times that by 60 here. What we find then is this corresponds to the nearest minute to 10 minutes. Okay, so 9.17249, what that gives me then is 9 hours and 10 minutes. So what we're saying then is this is 1 hour and 2 minutes since midday. So in that case then, the times here, so the times at which the height so this is the times at which the height of the seawater, let me just double check I'm getting this grammatically correct then. The height of the seawater will be 6 meters, yep. This will be, so 1 hour and 2 minutes, that will be 13:02. Remember, this is since midday, so this will be 13:02. And then we're going to have, so 9 hours and 10 minutes, that corresponds to 21:10. Okay, we're giving these as times here, so 13:02 and 21:10 there. Okay, there we have it, so that is the solution to part B. And we're nearly done now, the very last part of this exam paper here, part C. It just says state one limitation of the model. So one limitation of the model here, there's a few different things you can say really, but I think the easiest or the most obvious limitation here is that the model doesn't take into account the seasons. So the height may vary with seasons, okay, or the weather. So height may vary with the seasons / weather. Okay, that would be absolutely fine there. It's just one mark, it's just looking for one limitation, and that is absolutely fine. But like I said, there's a few different things you can write there. I think that's the most obvious limitation there to the model for this question. Okay, and there we have it. So that brings us to the end of this question, and that brings us to the end of this exam paper. So this was paper 1. If you've made it this far, well done. This has been quite a bit of a slog, but we got there. So thanks for watching. Hopefully this has helped, and good luck with your upcoming A-level maths exams.